Justin is also pursuing his PhD in computer science at New Mexico Institute of Mining and Technology, focusing his research on the ways that users interact with personal security tools. Please join me in welcoming Justin to the stage.
Thanks. All right, hi everybody. It's been a nice long day. We're getting close to the end of it. That's great. So they listed this presentation as a hybrid data / business. We're gonna go a little more on the business side. There's not a whole lot from a really technical perspective to present here. So a little bit of background. At Los Alamos National Laboratory, you may or may not be aware, the primary mission is nuclear weapons technology and development. But the lab also has quite a large staff of cybersecurity researchers and cybersecurity specialists in other areas. So currently, I lead the application security team for the Software and Application Engineering Division, which does some commercial off-the-shelf, some business applications, and a lot of bespoke application development for different business areas around the lab. So we can, where's my clicker thingy here? Oh, is this it? Great, here we go. So the talk that I'm going to give to you today is called AI and Static Code Analysis, the Future of Application Security. Fancy title. We're going to talk about static application security testing. I do have to give you sort of the required disclaimers here. The United States government, nor any agency thereof, nor any of their employees makes any warranty, blah, 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 about any of the stuff that I'm going to talk about here today. Referencing any specific commercial product doesn't necessarily mean that we're endorsing that. And also, my views and opinions are mine and mine alone. We already talked about that. So at Los Alamos, we've ran into some challenges with developing secure applications. And a lot of what we've done to mitigate some of those security risks is relying on commercial off-the-shelf products. We're using F5 Big IP and their application security management functionality. We're doing a little bit of secure developer training. And most of it is just kind of trying to wrap our applications in a little secure bubble. We don't really have anything sort of on the ground at the developer level that's increasing our security posture in our application development. And the reason being is that developers usually aren't security practitioners unless you spend a lot of time and money training them up to be security practitioners, or somehow you get a security practitioner that just decides to become a developer, which is fairly rare. They're not security practitioners. They write code, and most of the developers that I know are pretty good at writing code. But they're not necessarily great at writing what we would consider secure code. And it's easy, it's really easy to write a vulnerability into your code without necessarily noticing it. Because in order to really notice a vulnerability in source code, you have to have this broad understanding of how every line of code that you've written operates by itself and in conjunction with the other lines of code that you've written. And so having tools that automate that process for you is really important. Mandatory peer review might catch some of these things. 2 sets of eyes is better than 1. But we see maybe 90% of vulnerabilities still passing through manual code review by a human. So the reason for that is because that code review is performed by developers. Most of the time, security practitioners aren't developers, don't come from a development background, and so they don't necessarily know what to look for in their own source code to determine whether it's vulnerable or not. Your security folks need to be really good developers if you want to include them in that code review process, because how many people in the audience here use multiple different languages to write applications within your organization? Pretty much everybody, right? At Los Alamos, we do a lot of development in Java, but then we have a little bit of everything else, ranging from Fortran to Go, Python. I think I saw somebody coming up to me a couple months ago with a question about securing ADA. When's the last time that we've actually used ADA in production? In the US government, currently, still. Yeah, so, you know, and it's really hard for a single security practitioner to be fluent in all of those languages to provide good security oversight with manual code reviews. Really, you need a dedicated person per language. And I don't know about any of you guys, but I certainly don't have the budget to hire that many people. So, and again, you could have the most security-minded person who's an amazing developer. You know, you have a perfect individual who speaks every programming language in the world and is 100% knowledgeable about cybersecurity. They're still going to miss something because they're people. Oh. So we do have automated code analysis tools out there. We're all familiar with static application security testing and its dynamic counterpart. So static code analysis automates the process of looking at source code line by line. A lot of times, though, it's just looking for a dictionary of specific functions that have been flagged as vulnerable, and you still have to go back and manually verify whether or not that's a vulnerability. We'll get into that a little bit more. I'm getting ahead of myself here. One good thing about static analysis tools, though, is that they often have a plugin for your IDE, whatever that might be, that gives that instantaneous feedback to the developer. When they're writing a line of code, we can say, hey, this line of code might not necessarily be secure. The developer can go back and try to refactor that in a more secure way. And then we have dynamic code analysis. This is basically after the code's compiled, we start analyzing that. We can look at control flow issues, memory leaks, sensitive system calls, and stuff like that. We use this a lot also for web application vulnerability testing. So there's a couple of different static code analysis methods that I'm going to call the traditional methods. First is data flow analysis. Data flow analysis is basically dividing the code into blocks, with each block having a defined entry point and a defined exit point. And the data flow analysis tools map out the flow of data both within the block itself and between blocks, and basically attempts to determine the outcome using tokenized pieces of data going through each of those data control blocks. This is pretty useful for basically seeing where your data is going and how your data is being accessed. Then we also look at taint analysis. And taint analysis is talking about user-controlled input. So we're just checking to see if that input is tainted. Has it been sanitized or not? And then we're basically attempting to trace the input to vulnerable functions, which we call sinks. A vulnerable function is a sink. And so the way that traditional static code analysis tools work is that once a vulnerability has been identified, it's flagged based on a list of rules or the sinks, the vulnerable functions that we're talking about. You get that list. The tool's going to present some suggestions to solve the issue. It's up to the user, which many times with this type of tool is, again, the developer, to decide whether or not that's a false positive. And then they have to identify the correct action to take to remediate that issue. So it's a lot of security-specific stuff that needs to be done by a development professional. So this is a very basic example of vulnerable code, and you have to forgive me. It's been a while since I wrote this. This is just basically, this is a command shell. So we're taking the input from the user, which we're expecting to be a file name, and we're piping it out to the command line cat command, which will dump everything out to standard output. However, if we look at that, line 12. Line 12, is anybody here a C programmer? Any of you C guys recognize what's kind of wrong? What am I doing insecurely here in line 12? George, you got an idea?
You're not checking the length of the buffer?
Yeah, well, I'm not specifying a maximum length for the buffer. That's kind of one thing. So that could result in a memory overflow. Stern copy actually doesn't properly null terminate strings either. So that's going to be an issue when we run through a little bit later. Line 13 is specifically where we're taking our user's input and we're just using it directly. We're not even bothering to sanitize it. And then sterncat also isn't memory safe. So there's an off by 1 issue here where you're going to be overwriting your memory buffer and overflowing again, potentially. And then in line 15 is where we're making that system call directly. So we're taking whatever that user has typed into that command line, and we're passing it directly to a system call. So the easiest way to, the easiest way, I mean, number one, that's probably not going to do you too much good in today's modern Linux systems, right? But if we have read access to the shadow file with this executable, if it's running as set UID as root, we could potentially spill out everybody's password hashes, right? Let's see, that was line 15. So here's an example of what this actually does. All right. So we have our file called test.txt, which just has a bunch of text inside of it. That's great. That works as expected. Now let's run that again. What we've done is thrown a semicolon onto the end of that there and run ls, which is now doing what we expected. It's dumping out the contents of our test file to standard output, but then it's also running the command after that semicolon. So basically, this is just going to allow a malicious user to take our program that was meant to be convenient for us and string together a whole bunch of commands and see what happens. But if we go back and look at that code, most of us here who are seasoned C developers, wait, where am I? There we go. Most of us here who are seasoned C developers, probably the first thing that popped out was the use of that system command. But the other stuff is hard to identify unless you're specifically looking for it. And so this is why using humans to do this code review is probably not the greatest strategy. So let's catch back up here. So here we can look at the logic of traditional analysis. An example rule. If our line contains argv, that says that we're checking the user's input. And the line does not contain main, because we need to specify argv as parameters in our main function definition. Then we're going to say, hey, you're directly using user input. Make sure you're sanitizing it. But you're going to end up with a lot of false positives for that because, well, number one, what happens if I am actually sanitizing it in that line? You're still going to give me an error. Hey, make sure you're sanitizing your input. And users are likely to get overloaded with all of these false positives and just start ignoring them. This happens in every situation. I couldn't tell you how many daily reports I'm sending out that people have rules that just immediately go into their trash, right? And so rules also can't understand the intent of the developer. So code that looks OK to a developer or to even a code reviewer still might not be good because it's not actually doing what you think it's doing. So we have a function here called calculate area, and we're returning length plus width, which is not, in fact, the area of a shape, right? So that could cause some logic issues later on in your application just because that's not the intent. Then there's no tool out there right now that can look at this and say, hey, you're calculating the area, but you're not returning a multiple of those two parameters. What was the intent of the code? So the way that we can improve this then is by building AI into the process. And what do I mean when I'm talking about AI? We'll get to that in a minute. But this is the manual labor step here. In order to improve this process, somebody somewhere is going to have to do some work. We're already working on some of these things at Los Alamos in our cybersecurity research group. And we have a couple of proof of concepts that we've been testing out with Java. And we're having some pretty good results so far. But basically, there's two steps in moving forward with this. And the first one is threat identification. How do we intelligently assess the threat that we're looking for before we analyze the code? So we can do this with decision trees. using training data from known vulnerable code, we can see what kinds of threats exist there. Some of this is going to be the same as the traditional methods where we're going to say, well, you know what, the system function call, that's always vulnerable. We shouldn't really be using that for anything, and there are ways to get around that. And then once we've got those threats identified, then we move into our code analysis phase, and we can use expert systems here to take that to the next step. So we take the outcomes of the decision trees and use those to create an inference rule set in our expert systems. Somehow my presenter view got a slide off from where I'm actually at, but that's OK. I'll just squint. So this is basically a decision tree model from a SQL injection attack. We're checking number one to see, has the input been sanitized? If the input's sanitized, we're not vulnerable to SQL injection because we've done our job there. That's it. The next thing that we're checking to see is, has the input been validated? Validation is for correctness of input. Is the input what we're expecting it to be? If yes, then we're not vulnerable to SQL injection. If no, again, well, are we using a prepared statement? Prepared statements are nice because they allow you to take user input, plug it in as a variable into a statement, and not really have to worry too much about that doing something you're not expecting it to do. So if we're using prepared statements, then again, we're not vulnerable. But if not, are we using a direct database call? Probably, since we weren't doing any of those other things, then yes, we're vulnerable to SQL injection. If not somehow, then maybe we're not. But what we do is we take the results from those decision trees, and we use it to create an inference rule set. So number one, if my input contains special characters, we're going to flag that as bad input. That's a validation step. If our input has been flagged as bad input and hasn't been sanitized, we're going to call it unvalidated. And if it's bad input and hasn't undergone validation, we're also going to call it unvalidated. If it's unvalidated and we're not using prepared statements, then we're going to call that potentially vulnerable. We're getting really close to making that decision that this is a vulnerable piece of code. Now, if that input is potentially vulnerable and it's passed directly through a database call, then yes, this is a vulnerable piece of code. So this is how the inference rules in an expert system work. And this is a very, very basic example for SQL injection, right? In practice, we've seen when we're building out our expert systems that our inference rule sets for a specific vulnerability are on the order of 50, 60 rules to identify one vulnerability. Luckily, many of those can be generated automatically from the output of those decision trees. So once we get into that kind of complicated building the expert system, like I said, 50, 60 rules just for one vulnerability, we need to kind of tighten it up a little bit and streamline that process, because writing that many rules to cover every potential line of code that could ever possibly be written, obviously we can't do that. So it doesn't really make sense to test every block of code. So we can use some text mining features like bag of words or something like that to determine which blocks of code might need to be tested. Or we could even just use regular expressions, right? So what we're going to do is we're going to identify a block of code. In some languages, that's easier than in others. Some languages get really finicky about white space determining what makes a block of code. But let's look at C, right? We have curly braces. So we can say, you know what? Every set of curly braces is a block of code. And every subset of curly braces, like an if or a for or something like that, that's going to be a block of code by itself as well. And we can take that block of code, break it down into individual tokenized words that are in that block of code, compare it with our list of potential vulnerabilities, which we've developed using the decision tree model, and say, you know what? There's nothing in there that looks suspicious. We don't need to test this block of code. Move on. And then we can also use more specific conditions, right? Does the block contain known vulnerable sinks? Do you take user input? The possibilities are endless. And the detection methods for this are also endless. Basically, whatever works for you while you're developing the system. So what are the benefits of using an AI-based code analysis? Well, once we've got the model, we don't really need to have that dedicated human anymore. There is that upfront investment where you're going to need people who know what they're doing in order to help build out those expert systems. But if you think about the long-term benefits, that's actually a really good investment to make right up front. You can take those individuals and focus them on more important things other than combing through code manually. And also, it's going to reduce false positives. As long as we use a really good training set, which developing that is a challenge in and of itself, and I'm sure has been covered many times today. But once we have that good training data and we get our model well prepared, we're going to reduce those false positives. And what we're seeing right now with our work at Los Alamos is we're getting a false positive rate of about 3%, which is, when you're talking millions of lines of code, 3% isn't that bad. And again, this is proof of concept functionality, right? That we're in no way ready to go prime time with this. And so over the next few months or a year or so of development, we're hoping to get that down to as close to 0 as possible. So one thing that helps us moving in that direction, if there is a false positive and we're presenting that information to the developer with a plugin, so right now we have an Eclipse plugin that we're working with, in addition to saying, hey, we think this is a vulnerability, we're also providing a confidence level. So our model is 90% certain that this is a vulnerability. OK, that's worth putting in the effort to go back and fix it. But if we're only 43% certain that this is a vulnerability, maybe that's not that important to focus on. And you can maybe ignore that. But in that case, if we're talking about letting people determine a confidence level that they're comfortable with ignoring, you still need to put in that effort to train those individuals to be better security practitioners. And I will always, always support secure developer training, right? Because as we all know, as cybersecurity professionals, every individual user should be a cybersecurity professional, at least partly, right? So there are a couple of caveats to this, though, if you want to take this out in the world and start developing it yourself. Number one is the development of those expert systems. You need experts to help you with that. And unfortunately, research on the academic side into expert systems is kind of stalled because people have moved on to the newest, bigger, better thing, advanced neural networks and such, that is kind of more interesting, more rewarding, if you will. And there are also niche programming languages that you're going to write these systems in. Lisp, Prolog, Eclipse, those kinds of things. It's going to be difficult to hire expertise in that area because of bullet point number 1 there. So you're going to have to probably train it up. And you can't do this in a vacuum. Application security experts absolutely need to be involved. And so do the developers that you're trying to develop this tool for. And we still haven't solved the problem of developer intent. Our tool still has trouble deciding what the developer actually meant to do. And so for that, you do need to get developer input as you're going along. Only have about 2 minutes left here, so I'll go through this a little bit quickly. We all know that machine learning and artificial intelligence is a buzzword these days. There are a lot of products out there that claim to incorporate them that really don't. There aren't really any AI-based code analysis tools out there, which is why we started working on our own. Our goal is to go commercial first, but if we can't find something, we start developing internally. IBM has one called Intelligent Finding Analytics and Intelligent Code Analysis, and they have a really good success rate on par with what we're developing internally. But that's more focused on looking at the output of your traditional vulnerability management tools and then saying, hey, that's a false positive. So it's actually really good at finding false positives in other data. But that's not what we're looking for. We want something that just does it right there in one tool. So you guys know how to play around with some of this stuff. If you want to work on some of these simple models, take that SQL decision tree and expand it a little bit for your own purposes, download Orange 3. It's great, easy to use user interface. When you're not dealing with neural networks, if you were, TensorFlow would be the way to go, but Orange 3 is really great. You can use the text plugin there to do some of that text mining on code blocks, turning them into bags of words. And Eclipse is a great inference engine. It's a complete object-oriented language, and it was developed by NASA. It's very, very easy to start to work with. And so that brings me to the end of my presentation. Are there any questions? All right. Thanks.